All right, folks, Mr. Hansen here. We're going to take a look at the next step of actually creating the simulation to simulate airflow over our vehicle. So in the last tutorial, we looked at importing our design and creating an enclosure, a wind tunnel around that vehicle. I'm actually going to click my enclosure up here so that I can directly create a simulation for this particular design. Now, we are doing what's called incompressible fluid flow. So that's briefly just talking about airflow where we have relatively low speeds, not approaching like the speed of sound or anything, where like the gas, the air moving across our vehicle isn't going to actually like compress and create additional pressures on our design because this is not a super high pressure system. So incompressible fluid flow should work pretty well. All right, so I did hide all of my flow region sides. I'm going to right click and select show all just to have that. And if you want to, create kind of an X-ray view, you can use wireframe or, change the render mode up here. All right, we're going to leave all this stuff alone here in our setup for incompressible fluid. Let me go ahead and rename this design one. Let's call it design one sim. Our geometry should already be loaded in. We're using that design one stock body where we have all those faces and the enclosure that we created. Materials, the first thing we're going to set up, and this is essentially going to be what makes up the inside of our wind tunnel. That's just going to be air. And so you're familiar with the drag equation, depends on air density. So, that's already set up for you. And we want to make sure that's applied to our flow region, the box surrounding our vehicle. All right. Don't have to worry about any of these initial conditions because everything's starting at 0. But what we are going to have to do is set up some boundary conditions. And so boundary conditions are essentially telling us what's happening at each of these different surfaces, the boundaries of our flow region, our wind tunnel. And so the first thing is this front face here is going to be a velocity inlet. And that's where air is going to be flowing into the wind tunnel. So fixed value, I want to select on that front face. We got to think about what direction the air is going to be moving. So the air is moving from this front face to this back face, and that is in the negative x direction. So here where you see ux, I want that to be negative. Let's go with 20 meters per second. That's probably a little bit fast for our CO2 racers, but this should work well for our simulation. And as long as we're using the same speed and the same direction relative to our racer, we should get a good comparison between the different designs. So velocity inlet, fixed value, that's my first boundary condition. Now, we're going to set up some walls. And so obviously, the sides are all going to be walls, but we're going to treat them as something called a slip wall. And that's just where, if we think about our wind being a particle, they can slip through those walls and it's not going to actually impact the pressures building up over this vehicle. And so I want to select the three walls, 2 on the side, 1 on the top, and those are going to be slip walls. And then at the back here, this is where the air is going to escape. And what I'm going to try and do with the air escaping is keep that pressure at the back wall essentially 0. That'll let all the air that comes in go out the back. And so we're going to treat that as a pressure outlet. And so that's going to be the back face of my wind tunnel. We want that pressure to stay consistently at 0 pascals. Pretty simple. All right. Now, if we think about this as a car that is moving, in this case, based on my view cube down here in the positive x direction, we're going to think about the floor moving backwards in the negative x direction. And so what we're going to create is another wall for the ground, except this is going to be a moving wall. So let me select just this bottom edge. And that, in this case, that's going to be moving essentially, with the air. That's the ground moving relative to the car. So I'm going to make sure that's the same as the wind moving over the vehicle. So that's a moving wall on the bottom edge. And last but not least, we got the vehicle body itself. And that's going to be another wall. This is going to be a no-slip wall. So this is where we actually want to see the interactions of the air particles interacting with the vehicle versus the slip walls on the side where the air doesn't interact with those sides. And so here on faces, since I created this topological entity set, I can select my design one body, piece of cake that'll select all the sides of this guy. Hit the check mark, and now we got our boundary conditions set up. So that should at the very least be enough to get started with our simulation. Let's not mess with any of the numeric solver information. Let's make our maximum runtime. What is it? Instead of 10,000 seconds, let's make that 1,000 seconds. That'll save us a little time on the front end. All right. All right, so that is enough to actually set up our simulation as far as the physical body of the car is concerned. Now we got to think about what kind of data we want to collect. And so if you look at results control here in our simulation setup, there's a bunch of stuff here, super duper. But what we're concerned with is what's called the drag coefficient. We want to figure out the drag coefficient of this vehicle. So I'm going to go up here to forces and moments, and I want to calculate the force and moment coefficients. And so here we have to be a little bit careful. You'll see a little dot pop up. That's where it's using this, calculating the center of rotation, but that's not actually the center of rotation of my vehicle. And so to get that precise center of rotation, I'm actually going to have to go back to Onshape and take a look at my design in Onshape. And so before you can calculate this center of rotation, which is also the center of mass of our vehicle, we're going to have to assign a material to our part. So back in Onshape, I'm going to go to Assign Material. And in the library, I chose basswood for this because that's probably what we'll actually build these things out of. It's a nice, strong hardwood. So you can select basswood, save that, super duper. And then if you go down here to the mass properties, let me click my part there. You'll see where it says center of mass. That's going to be the same as the center of rotation for our vehicle. And so these are the numbers that you want to punch in for X, Y, Z over here in my setup for center of rotation. So we want those to, let's see. All right, negative 1.09. So negative 1.09. That's not in meters in my Onshape document. That's actually set up in inches. So I'm going to select inches there. Let's see. 0 for Y and 0.967 for Z. Inches for Z. All right. So that's moved my center of mass to what looks like more like the middle of this vehicle. Lift direction is going to be which direction is up, in which case this is going to be the Z direction. So you should see a 1 by that Z direction. And then the drag direction is which direction the drag force is going to push. And so if my vehicle is moving, looking at this view cube in the positive X direction, my drag direction is actually going to be in negative X. So I'm going to put a negative there, indicating that my drag's backwards from how this is oriented. And our pitch axis is just going to be the Y axis. So you can leave a 1 there where it says Y. Now we got a few more things to set up. Free stream velocity is the speed at which our stream of air is moving across the vehicle. We already decided this is in the negative X direction at 20 meters per second. Reference length and reference area value are two things. Again, I'm going to have to go back to Onshape to figure out. So my reference length, I mean, it's pretty simple. It's just the length of my vehicle body. In this case, the measure tool tells me right there, if I click on that bottom edge, it says 12. You could click, a front point to back point, and that should give you a good estimate of what your overall length is. So let me punch in 12 inches for my reference length. And for reference area value, that's where we're looking at the front area that we want to calculate the drag for. We have a slightly extra step here. I'm going to view my vehicle from the front, which in this case is the right plane. Now you can't just click those because what we need is the projection of this front view on the right plane. I want to figure out what the area of this big old, this big square in this case for this particular design. So one easy way to do that is to create a sketch on whatever plane is facing the front of your vehicle. And I'm going to use the use tool, the project tool, to get all the outside edges. And now if I hide my body, I've got a shape that represents the front view of my vehicle. And if I click that, Onshape's going to tell me the area of that shape. So that's 8.25 square inches. So again, let me plug that down here, 8.25, not in meters squared, of course, inches. And my reference length is definitely not 12 meters, that's 12 inches. And again, under faces, I want to select my design one body because that's what I'm calculating the drag coefficient of. All right. Oh, let's make that 20. I forgot, I already set the direction of the drag in the drag direction, so that should be 20 meters per second. Cool. All right, so we've set that up. Now we're actually ready to run our simulations. Now, before we run our simulation, we're going to have to generate what's called a mesh. Blah, 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 blah. Don't worry about any of those details. Just go ahead and hit generate. And when you hit generate, again, this is going to be a computationally intensive operation. It's going to take a second to run, but let me just show you what you guys are going to get. The mesh is, you'll see kind of like a funky grid all over your flow area. And if I change the view mode here of the vehicle inside, and these are all the points that we're going to try and calculate values for, like forces and speeds and all the details that we're trying to calculate. And so again, you can see why this is so computationally intense. There's a lot of three-dimensional points describing both the box and the car inside that. So give that some time to run. You'll have your mesh and you'll be ready to run your simulation.